Today we're going to learn about sequences and series. So let's first look at sequences. So what is a sequence? You can think of a sequence as a set of objects that is ordered. So what do we mean by that? Well, in this set, when we say that they're ordered, that means order matters. So each object has a certain place in the list. So you have a first term, you have a second term, you have a third term, and so on. So each object is actually called a term. And like I said, they have a position, they have an order. And so you can think of a sequence simply something like this, where let's say we've got 3, 6, 9, 12, 15, and so on. That's a sequence. 3 is called the first term, 6 would be the second term, 9 would be the third term, 12 is the fourth term, and so on and so on. Another one that is very famous, you've probably heard of the Fibonacci sequence. And the Fibonacci sequence, that one starts with a 1 and a 1 and a 2 and a 3 and a 5 and an 8. And if you've never seen it, it may seem like, where the heck are these numbers coming from? But it turns out that there's actually a nice easy pattern. Where they're coming from is the sum of the first, or the previous two terms added together gives you the next term. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, and so on. So there's a list of numbers, but there's a definite order to the numbers. The first term is 1, the second term is 1, the third term is 2, fourth term, fifth term, sixth term, seventh term, eighth term, ninth term is 34, and so on. So that's all a sequence is. It's just a list of numbers, and they have an order to them. So now that we know what a sequence is, let's just look at the input and the output, so the domain and range. The domain of a sequence, you may be going, well, what are the inputs? It's just a list of numbers. How can you have an input and an output? Well, the domain of the sequence is simply, it's the set of integers. And most often, it's actually the set of natural numbers. I'll describe this in a second. But then the range of the sequence, this is the set of terms. And basically it's any complex number. So what am I talking about there? Well, let's take a look at the Fibonacci sequence, for instance. So the Fibonacci sequence, we have the input and we have the output. So the first term was 1, the second term was 1, the third term is 2, the fourth term is 3, the fifth term was 5, the sixth term was 8, the seventh term was 13, and so on and so on and so on. So the input, you can see, it's just these list of, in this case, it's the natural numbers. Natural numbers start at 1 and just go up by 1. 1, 2, 3, 4, 5, 6, 7. It's the numbers you naturally learned to start counting with. That's why we call them the natural numbers. The range is a set of outputs, and so that is the actual sequence itself. So 1, 1, 2, 3, 5, 8, 13. So there's your output. And so we have, that's your domain and range then, your input and output. So this is the domain, and this is the range. Now, I'm going to say one thing That might get a little confusing, but then we're going to kind of drop it. But what gets a little confusing is that input, is the domain. Because why didn't I just say up here the domain is the set of natural numbers? Why did I say set of integers? And that's because when we're actually using these things in practical applications, sometimes it's convenient not to call the first term 1, but maybe you're going to call the first term 0. So the 0th term. So you start counting at 0 and you go 0, 1, 2, 3, 4, 5, 6, 7. Occasionally, it actually sometimes makes more sense to start with negative numbers. Maybe you start with -2 and then go to -1, 0, 1, 2, 3, 4. So your domain actually could start at any integer, but then it's going to just increase by 1 each time. And so that's why I say the set of integers. For us, for this year, we're going to start with the first term is always 1. It's just a little easier that way. So when we're talking about that. But it just depends on the situation. Okay, so let's take a look at explicit formulas versus recursive formulas. Okay, so we're going to look at explicit rules. They're also called general rules, rules for the nth term. All that means the same thing. And then we have something called recursive formulas. So what are the difference here? Well, let's take a look at this easy one. That we looked at above, 3, 6, 12, whoops, can't count, 3, 6, 9, 12, 15, and so on and so on and so on. So it's just the multiples of 3. So an explicit rule is going to be just a formula to find the nth term. So what does that look like then? Well, let's try to look for patterns. When you're looking for an explicit rule, you're going to try to look for patterns. Sometimes it helps if you don't see it right away. Make a table of values and try to come up with rules. You may have done something like this actually when you were learning about XY tables, T-charts, graphing back in the old days when you were just a wee little one. But I'm going to make a T-chart that looks like this. Now I've used a new notation here. So N is going to represent the term. So we have the first term, the second term, and the third term, and the fourth term, and the fifth term. Those are the known ones here. A sub N is the nth term. So in other words, when N is 1, we have A sub 1. So we have the first term. So that's A sub 1. And the first term in this case is 3. And then when N is 2, then we have A sub 2. And in this case, the second term is 6. And so on. The third term, A sub 3 is 9. A sub 4 is 12. And finally, the fifth term, A sub 5 is 15. So what you're going to want to do is, if it's not obvious to you, you're going to want to try to find a way to rewrite these using the 1, 2, 3, 4, 5. And in this case, it's pretty easy. 3 is the same thing as 3 times 1. 6 is the same thing as 3 times 2. 9 is 3 times 3. 12 is 3 times 4. 15 is 3 times 5. So to find the first term, you multiply 1 times 3. To find the second term, you multiply 2 times 3. To find the fourth term, you multiply 4 times 3. So if I want to find the nth term, then the nth term is 3 times n. And that's my explicit rule, explicit formula. A sub n equals 3n. Boom. There we go. That's all there is. So this isn't always so easy, finding the pattern. But once you find the pattern, then a strategy, everybody has their own ways of doing this. It's kind of like puzzles. So, it's just, there's no one rule that you're always going to do. But a strategy that you can do is, once you figure out what the pattern, once you know how to describe it, like it's just the multiples of 3. Okay, it's multiples of 3. So now let me see if I can rewrite each one somehow using a 1, 2, 3, 4, 5, but everything else stays the same. and then you can find the nth term. And that's an explicit rule, like I said. Explicit rule lets you explicitly find any term. Now that we have the explicit rule, now we could, for instance, find the 100th term. And it'd be really easy. The 100th term is when you let n equal 100. And so in this case, it's going to be 3 times 100. So the 100th term is 300. Now this one was a really easy example, but if the formula was a little more complicated, this gives you a nice easy way to find a specific term. That's an explicit formula. Now let's look at what a recursive formula looks like. So let's find a recursive formula for the Fibonacci sequence. So let's just write it down here. 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. If you tried to write an explicit rule, this one's really complicated. In fact, I can't remember what it is. You can Google it. It's not an easy thing to see what the explicit rule. Like if I wanted to know what the 100th term is of the Fibonacci sequence, I'd have to go and do this pattern 100 times to find the 100th term. That would be really tedious. But there is another type of formula that can describe a sequence. In the Fibonacci sequence, it's really easy. Basically, remember what you do to find the Fibonacci sequence. Any term is the sum of the 2 previous terms. So 3 is the sum of 2 plus 1. The 6th term is the sum of the 5th and the 4th term. The 9th term is the sum of the 8th and the 7th term. So it's really easy to describe that way. If you can ever describe a sequence by what you do with previous terms to find the next term, you can write a recursive formula really easily. So the way a recursive formula looks like is this. There's actually parts to it. There's 2 parts to the recursive formula. You have to say, where do you start? And you have to say what you do each time. Now, the Fibonacci sequence, you actually need to start with the first 2 terms. Because if I try to do that rule of to find each term, you add the 2 previous terms. If I'm starting with the second term, I don't have 2 previous terms yet. So I have to define the first and the second term, but then I can go to my rule and say, to find the third term, you add the 2 previous terms. To find the 4th term, you add the 2 previous terms, and so on. So my where to start in this case, I have to give the first 2 terms. And so I just say, the first term is 1, the second term is 1. Now I've defined where to start. Now I have to say what I do each time. And so what do I do each time? Well, to find a term, you add the 2 previous terms. So let's see what this looks like then. And there's different ways you can do it, but it's typically done like this. Now, I don't know why a lot of times you'll see people switch from n that we used in the explicit formulas to k. It really doesn't matter what variable you use. It's just we're typically going to use up here for the explicit formulas, we typically use n's. For recursive formulas, we typically use k's. It's just kind of a standard. So each term is the sum of the 2 previous terms. Now, how are we going to write that? Well, what comes right before k? K minus 1. And then what comes before k minus 1? K minus 2. And so this is saying a term is the previous term plus the second previous term. And then that's it. And then what we do is we actually bracket these. So let me put that in blue. we bracket these together to show that all of this goes together as one rule. So you have to say where you start, and you have to say what you do each time. And that's a recursive formula. In recursive formulas, sometimes it's nice to see what you do each time to get the next term. Sometimes it's nice to be able to just jump really quickly to a specific term. It just kind of depends on what you're doing with them. Let's just look at the recursive formula for that one we were doing above. 3, 6, 9, 12, 15, and so on. So we know it's the multiples of 3, but remember when you're doing a recursive formula, you want to be able to describe what you do each time. So what do I do each time to get to the next term? To go from 3 to 6, I add 3. To go from 6 to 9, I add 3. To go from 9 to 12, you add 3. To go from 12 to 15, you add 3. And so you're just adding 3 each time. So our recursive formula, we have to say where we're starting with. And in this case, we only need the first term. Once we know the first term, then each time we add 3. Now think about this. If you want, you can pause the video. But each term is the previous term plus 3. And there you go. That's the recursive formula. Now I also want to show you there's a slightly different way that sometimes you'll see it, and really it doesn't matter. You just have to know how to read each way. You're still going to have those two parts. You're still going to say where you want to start and then what you do each time. So we still have to say we're starting with 3. The first term is 3. But then another way of saying, rather than saying each term is the previous term plus 3, you could say to find the next term, you take the term plus 3. So the next term would be a sub k plus 1, and then we say a sub k plus 3. A term plus 3 is equal to the next term. So you just have to know how to read these subscripts. So I like to think of a sub k as the term, and then if you're adding one, it's the next term. If you're subtracting one, it's the previous term. But each one of these things says the same thing. So put these together, and this is another recursive rule. So a term is the previous term plus 3, or a term plus 3 is equal to the next term. It says the same thing. So that's recursive formulas and explicit formulas. So now let's look at an example. Let's look at writing the first 5 terms of the following sequences. And if you want to pause the video and try these on your own, that would be ideal. There is something a little special in the third one. There's this exclamation point that you may not have seen before. It means factorial. Don't worry about it if you haven't seen it yet. I'll explain it when we do the problem together. It's nothing special, but you don't say it n. It's n factorial. But at least try the first 2, and then we'll come back together and check our answers. So here's the first one done. And notice all you do is you just let all these n's equal a 1, equal a 2, equal a 3, 4, 5, work it out, and there's your terms. It's nothing more complicated than that. Okay, let's look at the second one. Okay, this one, same exact thing. You let all these n's equal a 1, a 2, a 3, a 4, and 5, and so on, and then you end up with these values. One thing I want you to notice about this one is see how the terms alternate signs? -3, +4, -5, +6, -7. So negative, positive, negative, positive, negative. If you ever see the signs alternate and you have to write the explicit formula, this is a little thing to know. That means you're going to have a factor of -1 to some power. And if you start with a negative, then you're just going to have an n for an exponent. Let's say that these started with a positive. You're going to have to adjust the exponent to make sure that you start with a positive instead. You can make that n plus 1 or n minus 1. Those are typically what's used. But you're going to have -1 to some power, and that's what gives you those alternating signs. Okay, so let's take a look at part C then. Okay, so this is what factorial means. Factorial is, if you have 1 factorial, then you just start with 1. Let's actually jump all the way down to 5 factorial. So you start with the number 5, and then you multiply by each integer all the way down to 1. So 5 times 4 times 3 times 2 times 1. 4 factorial, you start at 4 and multiply all the way down to 1. 3 factorial, you start at 3, multiply all the way down to 1. 2 factorial, start at 2 and go all the way to 1. And then 1, you're just starting and ending at 1. That's all factorial is. And so then when you go ahead and work it out, the first term is going to be 5. The second term will be 5 halves. The third term will be 5 sixths. Then we have 5 times 24. And on the last one, we can actually just cross out the 5s and get 1 over 24. And so then, there we go. That's our sequence then. So we have 5, 5 halves, 5 sixths, 5 over 24, 1 over 24. And boom. So there's writing the first 5 terms using an explicit rule. Okay, so let's take a look at this one. Writing the first four terms of this sequence. Now I didn't say it, but you should be able to see from the notation that this is a recursive formula, not an explicit formula. First of all, there's 2 parts. That's a dead giveaway. But also this notation right here, we have a sub k plus 1. If you see an a sub k plus or a sub k minus, it's another dead giveaway that you've got, you're dealing with a recursive formula. Okay, so give this one a shot and then we'll take a look together. Okay, so there's my answer. And you may be going, wait, where's the work? Well, I'll show you how you could do it the long way, showing work in a second. But the nice thing with recursive formulas, they're telling you what to do. And so if you know how to read them, then you can just follow the rule. So the rule says start with -4. The first term is -4. So start with -4. So I started there. And then -4 times a term will give me the next term. All I'm doing is multiplying by -4. So -4 times -4 is positive 16. Multiply by -4 again, and you're going to get -64. Multiply by -4 again, and you're going to get positive 256. That's it. So you don't have to show any work, which is really nice. Now, let's say that you forgot how to read this and you needed to do it the long way. Then here's what we're going to do. So you're going to pick different values for k and plug them in. First of all, we know the first term is -4. Again, that's defined for us. To find the second term, I'm going to need the subscript to be 2. So I'm going to let k equal 1. I put a 1 in for this k. I put a 1 in for that k. And now it's telling me a sub 2 is -4 times the first term, which was -4. So I get 16. And then so on and so on. Let's just jump here. To find the fourth term, if I let k equal 3, then I'm going to have a sub 3 plus 1, which is a sub 4. And that's going to equal -4 times a sub 3. So I let this k equal 3 and that k equal 3. So now I know the fourth term is just -4 times the third term, which was -64. And I get this. So you can work it out the long way, but you don't have to. That's nice. Okay, so let's look at this example together. Describe the pattern and write a rule for the nth term. Not sure why I capitalized pattern. Oh well. All right, so see if you can figure this one out, and then we'll take a look together. So this time it says write a rule. That implies, by the way, they want an explicit rule. If they ever want a recursive rule, they'll specify the word recursive. Otherwise, assume it's talking explicit. Okay, so pause the video and then try this on your own. There's actually more than one right way to write the answer here. So this is one possibility. Maybe you just saw, well, you multiply by -1/3 each time. And so if we start with 1/3, if I multiply by -1/3 the first time, I actually didn't multiply by any 1/3. So when n is 1, I want this exponent to be 0 to show the first term, don't multiply by -1/3. But then the second term, we're going to multiply by 1/3. The third term, we're going to multiply by 2, and so on. This could work. And this is definitely one answer. And it's a perfectly good answer. But you may have thought about it a different way. This could have been another way that you looked at it. Maybe you just saw that the signs alternate, and you start with a positive, and then the denominators are multiples of 3. So let's take a look at this then. So the signs alternate. That's that -1 to some power thing I was talking about. And in this case, you want to start with a positive 1/3. So when n is 1, you need to make this exponent even. And so just add 1 to it. When n is 2, now the exponent will be odd, so it's going to be negative for the second term. When n is 3, this exponent will be even, so now your third term is positive, and so on. So this part right here takes care of the alternating signs, and then the denominators are multiples of 3. So the numerators are 1 each time, and the denominators are just 3 to whatever power, 3 to the first power, 3 to the second. And you can actually manipulate this to make it equivalent to that. These are equivalent expressions. That's why they both describe the same sequence. So lots of different ways you can do it. There's more than just these two, but they both kind of they'll all boil down to some idea behind these guys. So there you go, writing the explicit rule. Let's look at a part B. Okay, this one might be a little trickier, but pause the video and give this one a shot. Write an explicit rule for this sequence. Okay, this one definitely gets a little trickier. So what I saw was, again, I made this one where I made the table. So the first, second, third, fourth term are 2, 6, 12, and 20. I could break these up like this: 1 times 2, 2 times 3, 3 times 4, 4 times 5. There's definitely a nice pattern in these factors. And hey, wait, 1, 2, 3, 4, 1, 2, 3, 4. So these first factors just match n, and each one of these is just one more. So you could think of it like this, or the first factor matched n, and the second factor was just one more. And so once you have that, you don't actually have the explicit formula yet, but you're on your way. All you have to do now is write it as 1. So the nth term is n times n plus 1, and you got it. So sometimes they take a little bit of playing around with before you can see what the pattern is. So they get a little tricky sometimes. All right. Okay, so let's take a look at a series now. A series is just the sum of the terms of a sequence. That's it. So I have things that I'm comparing here. I have an infinite sequence versus a finite sequence, a finite series versus an infinite series. So a finite sequence or a finite series, and here I should actually have the word finite here. Finite means it stops at some point. So notice I don't have the ... that I have here for infinite. Infinite means you don't stop. You just keep going. And so a series, you just take the terms of the sequence and you add them. So a sequence is a list of numbers. A series is the sum of the numbers in the list. That's the only difference. And then we have this other term called nth partial sum. We use this notation for it, a capital S with a subscript of n. And so that's the nth partial sum, and that means the sum of the first n terms. So if I have s sub 4, that's the fourth partial sum. That means take the first 4 terms and add them. And in this case, you get the fourth partial sum is 30. So there's just some terminology for you. Now let's take a look at another way to write sums, to write series. So let's just keep picking on this guy right here. 3 plus 6 plus 9 plus ... So continue that pattern. So another way to write that is using this symbol right here. It's a Greek letter sigma. It's called sigma notation or summation notation. So it's a Greek letter sigma. This is how you spell it. And so the way that we would do this, remember what the explicit formula for this guy was? Remember that 3, 6, 9, 12, and so on? That was a sub n is 3 times n. So we put that here. I'm just going to go ahead and put all these things here. In this case, it's infinite, so we're going to go to infinity. And so that's how you write it. Now let's take a look at some vocabulary here. I'm going to write this a little bit bigger. because each one of these parts has a name. So this part right here, the whole formula there, that is called the argument. It's a common word that we use in math. Basically, when you have some operator, in this case we have the sigma, and it's operating on this chunk, that's called the argument. We have this part down here, just the 1. That's called the lower limit. This part right here at the top, that's called the upper limit. And then finally we have the variable, and that guy is called the index of summation. And the way you read this is it describes exactly what you do. It's kind of a mouthful to read, but the way you read it is this. So it's read as the summation of 3n as n goes from 1 to infinity. And there's a little bit of order you can play around with. You can say 3n as n goes from 1 to infinity, or you can say the summation as n goes from 1 to infinity of 3n. So you can actually reverse these two things, and it says the same thing. So, okay, what does that actually mean? What that means is this. I'm going to go ahead and put it down here again. The summation of 3n as n goes from 1 to infinity. So that means you're going to take 3n, but let n equal 1. So you're going to start at 1. And then remember, n is not just equal to 1. Even though we write n equals 1, n goes from 1 to infinity. So it's starting at 1, but then it's going to increase by 1 each time until you get to infinity. So it's going to increase by 1, so you're going to have 3 times 2. And then you're going to have 3 times 3. And then you're going to have 3 times 4. And then you're going to have 3 times 5. And so on and so on. This is going to keep going. And this is the summation, so you put plus signs in between. And if you think about it, if you work it out, that means 3 plus 6 plus 9 plus 12 plus 15 plus da. And it is this series right here, 3 plus 6 plus 9. So you can write series using this summation notation. And get used to that summation notation. That's used a lot in math. It comes up a lot in calculus. So let's practice with that summation notation a little bit. Okay, so let's look at this example first. So write this in summation notation. And definitely pause the video and try this on your own. And we'll take a look at the solution together. Okay, so you're going to want to try to either figure out what the explicit formula is. So if you can just see that a sub n is going to be 5n, you can jump right down to here. But if not, try to rewrite each term so that you have everything else is staying the same, but the part that changes just increases by 1 each time. And it actually doesn't have to start at 1. I'll show you examples where it doesn't have to start at 1. But just whatever's changing goes up by 1 each time. So in this case, and notice also by the way, I used I instead of n. You can use whatever variable you want, doesn't matter. N, I, and k are most commonly used, but it really doesn't matter. So if I look at this now, I'm just multiplying 5 times a number, so that's my argument, 5 times a number. That number starts at 1 and it stops at 20. So it's the summation of 5i as I goes from 1 to 20. And that's it. There's your answer. Okay, so let's try this problem. Okay, so again, try this on your own, and then we'll look at it together. All right, so if you noticed, like again, you don't have to write this part out, but you can if it helps you see it. If you notice, the numerator is just 1, 2, 3, 4, 5, so that's just the first term is 1, second term 2, third term 3. Well, that's easy. The numerator is just the term, and then the denominator is just the numerator plus 1, so just add 1 to the numerator. But you can also write it like this if it helps you see it. Again, k is starting at 1, and in this case, since it's got the dot, 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 that just means you never stop. And so k is going to infinity. All right, there is our answer there. Okay, just a couple more examples now where you're going to try to find the sum. Okay, so here's 3 problems right here. Again, try them on your own, and we will take a look at them together. Okay, so for part A, it's the summation of 2i as I goes from 1 to 6. So just do what it says. Let I go from 1 to 6. So you're going to have 2 times 1, and then 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6. And then you're going to add it all up. And when you do, hopefully my arithmetic is good. You guys can correct me in the comments if I was wrong, but the answer is 42. All right, let's try part B. If you haven't already tried it on your own, pause the video first and then give it a shot. Okay, so here we go with the second one, and notice we're starting at 3 this time. So let k equal 3, then 4, 5, 6, 7. We're going from 3 to 7. So start at 3, end at 7. But then you just work out each term, add them all up, you get 145. Okay, the last one's a little weird, but go ahead and take a look at this one and try it out. Pause the video, we'll take a look at it together. All right, so what was going on with this one? Well, notice there's no variable in the argument. It's just 10. So what do you do with that? When n equals 4, where do you even put the 4 in? You don't. What does 10 equal when n equals 4? Well, 10 still equals 10. So this first term was when n equaled 4, and then we had n equal 5, n equals 6, n equals 7, n equals 8. We still have to look at going from 4 to 8, but this 10 doesn't change. When n is 4, 10 is still 10. When n is 5, the argument is still 10. When n is 6, the argument is still 10. When n is 7, the argument is 10. When n is 8, the argument is 10. So you end up adding 10 5 times, and you get 50. There you go. So that's a not so brief introduction to series and sequences. Don't worry, the second video, which is only the last video in this, there's only 2 videos in this week, much shorter than this one. All right, see you later. Bye.